So once the relief fluid passes the PSV outlet pipe, it shall combine with the relief gas from the whole plant in the relief header. Now let's take a look at this header. The header collects the relief load, and this can be either from a set of PSVs scattered through the plant or through a portion of the plant, or this can be through blow-down valves that shall depressurize the system. The PSV header should be sized to handle the highest relief load from among the PSVs and blow-down valves. This also applies on the flare knockout drum and the flare itself. So how would we determine the relief load on which we shall size the flare system? PSVs shouldn't open in normal operation, nor do we need to depressurize the system in normal operation. In addition, each PSV or blowdown valve is responsible for protecting a specific system. So if we size the flare header based on the total relief load from all PSVs and depressurization loads at once, this would be a considerable exaggeration, leading to a huge and unpractical flare system. That's why it's essential to study the relief scenarios and which valve is expected to open simultaneously with each other. And what is the scenario that shall result in the most significant relief load? The flare system should be sized to handle this scenario in order to ensure that all relief scenarios are covered and we shall not face any issue if any of these PSVs or blowdown scenarios has occurred. So, how do we know this load? In most cases, if a PSV opens, it's not expected to open simultaneously with other PSVs. This is common if some blockage occurred in a system of a control valve that failed due to mechanical failure. So in this case, if the PSV opens, it's expected to be the only one at that time. However, if a fire occurred in an area with adjacent equipment, or in other words, equipment in the same fire zone, then in this case, all PSVs in the area may simultaneously open if the fire was large enough to cause overpressure in the zone. In this case, the flare system's relief load shall be equal to the combined load from different PSVs. If the plant was subject to an emergency shutdown and depressurization ratio, then in this case, there may be even a larger relief load. If there is some power failure or instrument air failure in the plant, this may affect multiple PSVs and may also lead to a complicated scenario. That's why, when sizing the maximum relief load, it's essential to study the system well and determine the worst case scenario and size the system based on this scenario. This is done by building the FlareNet model to check whether the flare header design and arrangement shall fit all these scenarios. If it doesn't fit them, then we should redesign the system and ensure it works efficiently when needed. Otherwise, this shall affect the function of PSVs and may lead to an overpressure in the plant and consequently probable equipment failure. But what about normal operation? If there is no relief load, the flare shall stop. In addition, this can introduce air to the system, which can cause an explosive mixture in the plant. That's why it's important to add a purge line. Through this line, some gas is sent to flare with a minimum velocity of 1 or 2 meters per second to be burned and hence ensure the availability of the flare and to avoid air ingress into the system.